This lecture is an explanation of the mean value theorem for derivatives and Rolle's theorem. So to get us started, when you are driving a car and your speed is varying, as it always does, must you be doing the average at some point during the time you're driving? So you start off, you go 20 miles an hour, you speed up to 40, you're down to 30, you're up to 35. At some point during the ride, is your instantaneous speed the same as what your average was for the whole time? And the answer is yes, it is. You must be going through the average at least at one point, if not more. And we can talk about this in terms of the mean value theorem. Here it is graphically. So you have a function, and it has to be continuous on the closed interval from a to b, and open and differentiable on the open interval a to b. And what the mean value theorem says is basically that the slope of the tangent line must be equal to the slope of the secant line at least one place. So the slope of the secant line, that would be like your average speed, and the slope of your tangent line is your instantaneous, and they must be parallel to each other. They must be equal at least one place, if not more. So in this particular drawing, they are the same at two places. So here we have one place here, where they are equivalent. Now let's go back and take a look at how this actually is more rigorously in terms of a definition. All right, this is the mean value theorem, which we abbreviate MVT. If, number one, f of x is continuous on the closed interval a to b, and number two, f of x is differentiable on the open interval a to b, so it's smooth the whole time, then there exists at least one place at x equals c between a and b, so the open interval, we're looking at solutions in the open interval, such that the derivative at c is equal to f of b minus f of a over b minus a. Well, this expression is simply the slope between a and points at x equals a and x equals b. So what we're saying is the slope of the derivative must be the same as the slope of the secant line, which is what I just showed in the previous slide. So in terms of why we need to have these particular definitions, let's take a look at some violations of the theorem. Well, in this situation here, we don't have continuity, and clearly if we take the average, which is basically just connecting the secant line, there's no place where a tangent line is flat. Over here, it's not differentiable. There's a kink here, and so there isn't any place on either this part or this part which is going to be parallel to this secant line. So those are a couple of violations. Now here's some ways you would see problems stated. So you are given a function, and you were given an interval, and you're trying to find any and all solutions to the mean value theorem for this particular function on this interval. And so this is a polynomial, therefore it is continuous and differentiable on the interval. And so what I'm going to do here is find y values to go with these x values. I need the y values because I need to find the slope of the secant line connecting the endpoints. Meanwhile, here's the derivative. So what I'm going to do is take the derivative and set it equal to the slope of the secant line. So I do 0 minus negative 2 divided by 1 minus, 0 minus negative 2 over negative 1 minus 1. So that's the slope of my secant line. This is the slope of my tangent line. I set them equal to each other. And I get this quadratic equation down here. Go ahead and solve that, and you get two solutions, negative 1/3 and 1. I'm only going to take negative 1/3 though because I just want solutions in the open interval. So this would be my answer, and we can see this graphically. Here's the graph of the function. Here's negative 1 and 1, so there's my secant line, and you can see at negative 1/3, if I draw on a tangent line, they're just about parallel as they should be. All right, now we have the function x plus 1 over x, and we have the interval from 1/2 to 2. And so, again, I'll find the slope of the secant line, so the y values, difference in y values over difference in x values. And I plug those into this function, and I end up getting negative 1. So therefore, the tangent, I'm going to set equal to negative 1. So I first write it this way. It's easier to differentiate. And I get negative x to the negative 2 must be equal to negative 1. So according to the mean value theorem, because this is differentiable and continuous on the interval. Now at x equals 0, it's not continuous and differentiable. I've got an asymptote, but I don't care about that because I'm between 1/2 and 2. So because it fits the hypothesis of the mean value theorem, I know that there must be at least one place where the derivative is equal to the slope of the secant line. Set them equal to each other, and you get plus or minus 1 but we only want positive 1 because we want to be within the interval from 1/2 to 2. And here's the graph. So there's your function, and here's the secant line. If I draw on a tangent line, you can see they look parallel. One more example of mean value theorem, and then we'll go on to Rolle's theorem, which is sort of a special case of the MVT, mean value theorem. Okay, this is involving some trig. So going from 0 to pi, sine is continuous and differentiable everywhere, so that's no problem. So first I find the slope of the secant line, change in y over change in x, plug it into the function, and I get 0. So then I find the derivative and set it equal to 0. To solve this equation, I use this double angle formula up here. And now I've got a quadratic equation in cosine, and you can factor this, and you get cosine is -1, or cosine is positive 1/2, which gives you these solutions. Pi gives you pi over 3, 5 pi over 3. I only want the solutions in this interval, so pi over 3 is my only one I'm going to keep. Here's a graph, and you can see between these 2 points there's the secant line, it's flat, and right here at pi over 3, which is a little bit bigger than 1, flat tangent line, so they're parallel. Okay, back to mean value theorem one more time, and then we'll look at Rolle's theorem. Mean value theorem, you have 2 hypotheses, continuous and differentiable. Now notice the slight difference for Rolle's theorem. For Rolle's theorem, you add a third hypothesis, and that is that the endpoints have the same y value. Then there exists at least one place, x equals c, on the open interval a to b, that the derivative is 0, which makes perfect sense since for mean value theorem, if f of a was equal to f of b, this slope would be 0. So Rolle's theorem you can think of as a special case of mean value theorem. So here's Rolle's theorem. Again, continuous and differentiable, but this time the endpoints are the same y value. This is sort of like the way the last problem worked out. And then therefore the derivative must be 0 in at least one place. Here it is graphically. Here's our mean value theorem. What we can do is to make this into a Rolle's theorem problem, we simply create a new function where we subtract the secant line from the tangent line. We get a new function which will be the exact same as the old one, except that now we ensure that the endpoints have the same y value. And so we create a new function, and then once that's done, we can again slide x, and you'll see that there will be at least one place on the interval from a to b that will be parallel to this horizontal, so it'll have a 0 slope. So we got a few more of these new these points to create, and we'll have a new function. And now when we slide it, you can see that if we want to look for these spots, okay, here's one spot here, and of course it corresponds to the mean value theorem solution, and the other spot will be down over here. So Rolle's theorem can be thought of, yes, again, as a special case of mean value theorem. Okay. Violations would work the same way for Rolle's theorem. That is, if the endpoints are not the same height, then clearly in here you won't necessarily have a flat tangent line. It's important to realize also the converse of these theorems is not true, such as just because there is a place here that is flat does not mean that the endpoints have to be at the same height, which would be true if the converse is true of Rolle's theorem, but it's not. Okay, some Rolle's theorem examples. So we have a function, we have an interval. So Rolle's theorem has 3 hypotheses. It's got to be continuous and differentiable. That's 2 of them, and it is because it's a polynomial, so it's both of those. And the endpoints have to be at the same height. So if I plug in 1, I get 0. If I plug in 2, I get 0. So Rolle's theorem conditions are met. So now I take a derivative and set it equal to 0, and I solve for x equals 3/2, which is between 1 and 2, so that's my solution. Now for this one, it's continuous from 0 to 6, and if you plug in 0, you would get 0. If you plug in 6, you get 0, but it's not differentiable. There's a kink at x equals 3, so Rolle's theorem does not apply, so we don't continue that problem. Cosine will be continuous and differentiable from 0 to 2 pi, or everywhere really, and cosine of 0 and cosine of 2 pi are both 1, so Rolle's theorem should apply. So we set the derivative equal to 0, and we get multiples of pi, and so we choose the one between 0 and 2 pi, and so the answer is just pi. And this is it graphically, where here we have cosine x from 0 to 2 pi, and here's our secant line, and our tangent line is parallel to it at pi. Secant x has asymptotes, so there could be some potential problems with that, but between negative pi over 4 and pi over 4, there's no problem. So we check to make sure the endpoints are the same, and they're rad 2, so Rolle's theorem should apply. So therefore we take a derivative and set it equal to 0, and we have tan x equals 0, because secant x will never be 0, so we just have tan x is 0, which is again multiples of pi, and so we just get 0 for that. And graphically what's happening is right here. So what happens is, if you drew straight across here, then clearly your tangent line would be flat at x equals 0. Just a little bit more vocabulary that kind of goes with this section, because we're going to start doing more with this type of vocabulary, is the derivative with respect to time of displacement is velocity. So displacement is final position minus initial position. So if you go somewhere and come back, your displacement is 0. So derivative displacement with respect to time is velocity. Derivative with respect to time of velocity is acceleration. And your absolute value of velocity is your speed. So speed and velocity are a little different. Velocity is a vector. It has a direction. So you can have negative velocity. Speed is a scalar. It's just a straight number. And this will lead to the idea also of distance traveled, which we talk about when we get to integration.